Welcome back. Today we're going to be working on section 1.4 with rational expressions. To start us off, I have a few problems here that I would like for you to practice factoring. Remember, we talked about a lot of different methods for factoring, including your greatest common factor, factoring trinomials, factoring by grouping, factoring difference of squares, and difference and sum of cubes. So just keep in mind all the different methods as you approach these 5 problems. So pause the video and work on these and then check your answers on the following slide. You can see your answers to these problems that you've worked. The first one here, we have a difference of squares. So we have a similar parentheses, but just with opposite signs. The second one, you would use the greatest common factor method and take out this as your GCF, and you would be left with this expression here. Number 3, you would have the difference of cubes, so follow the difference of cubes formula. Here, your a that you would work with would be the cube root of that, of this 8x to the third, so your a would be 2x, and your b would be the cube root of 27, which would be 3. And then you would have a squared plus the a times b, and then the b squared. On the next one, you would need to do the bottoms up method in order to get that one factored correctly. And then the fifth one, because you have 4 terms, you would use grouping to factor that. You would not be able to factor this one any further because you have a plus sign and you can't factor the sum of squares. Okay, like I said, today we're going to talk about rational expressions, and this is section 1.4. We're going to be on this section for 2 days. Today we're going to look at the domain of rational expressions as well as multiplying and dividing rational expressions, and we'll save adding and subtracting rational expressions for the next class. Okay, so first of all, what is a rational expression? Okay, if we have the quotient of 2 algebraic expressions, then those are going to be called fractional expressions. And basically, that's just saying it's a fractional expression if our expression is in the form of a fraction, essentially. For it to be a rational expression, it's actually a fractional expression in which both the numerator and the denominator are polynomials. So if we look up here, this would be a monomial, so it would be a type of polynomial. This would be a binomial, so it would be a type of polynomial. So this would be a rational expression. This would be 2 binomials, and it would be also a rational expression. And here we would have a polynomial over a polynomial, so that one would be a rational expression. This one would not be a rational expression simply because a polynomial cannot have this radical in it, and so because the radical is in this, it would not be a rational expression. So in this section, we're going to be dealing with problems that involve expressions that look like the first 3 here. Okay, domain is the first thing that I want to talk about. And really, I want you to think of it like kind of like the user's manual for this particular equation. So it's going to tell us what we can and can't put into the equation, just like your user's manual tells you what type of oil to put in a car, what type of gas to put in a car, and it's not going to run if you don't do those things. So with a rational expression, we have to restrict our domain and other types of expressions as well. And we'll talk about different things that we can and can't put into our function. So if you think of it as this user's manual for the function, then I think you'll understand a little bit better what we're trying to do with the domain. Okay, so the domain of an algebraic expression is the set of real numbers that the variable is permitted to have. Okay, so this is saying what values can we put in for our variable. So there's a couple things to look for as far as restrictions. The first one is our denominator cannot be equal to 0 because we know that we can't divide something by 0. If we do, we have an undefined expression. So basically, if I'm going to give the user's manual for this expression here, or the domain for it, I need to tell somebody that they cannot put 0 in for x, because if they put 0 in for x, it's going to be an undefined expression. And that's why the domain is written like this. So it would be the set of all x, and this little line means such that. So the set of all x such that x is not 0. So it can be anything else, it just can't be 0. Okay, the second one here, expressions under the radical must be positive or 0. Okay, so essentially we want to make sure that whatever's underneath the radical gets set greater than or equal to 0. We know that we can't take the square root of negative numbers, and so therefore we need to restrict the domain in such a way that whoever's using this expression knows not to put negative numbers in for x. And so our domain on this one will be the set of all x such that x is greater than or equal to 0. And if you were writing that in interval notation, our interval notation for that would be the bracket 0 to infinity. On this one, I didn't mention it, but another way to write this in interval notation would be negative infinity to 0, and then we'll union that with 0 to infinity. So when we do it like that, 0 is the only value that's actually excluded. So if you're asked to write it in interval notation, you'll write it like this. Okay, this last one here that we have, it's a combination of the two. So we have a radical, but we also have it in the denominator. So we've got to combine these two domains together. So x can be greater than or equal to 0, but it actually can't be equal to 0. So that's why we take the equals part off of this. And the last one we'll get to in chapter 4, and that is that you can only take the logarithm of positive expressions. We won't really be working with number 3 at this point. It'll be coming later in the course. Okay, so a few domains for you to look at here that we're going to go through. The first one is simply a trinomial, a quadratic. Anytime you have a polynomial, our domain is going to be all real numbers. So we're going to write it as negative infinity to positive infinity. The second one here, we're really not concerned about the x in the numerator. It can be anything. The denominator is the place that we're concerned about because we need to figure out what can x not be. What is it that we put in for x that's going to cause our denominator to be 0? So what I'm going to do is I'm going to say x minus 5 cannot be 0. And then if I solve that, I'm going to get that x cannot be 5. So in interval notation, that would be negative infinity to 5 union 5 to infinity. WebAssign is going to expect it usually to be written like this. In general, I think this is probably a more accepted way of writing it, but either will mean the same thing. Okay, this is another one. This x doesn't cause us problems. These in the denominator do. So the first thing we're actually going to do is factor this. Okay, so we need the factors of 6 that add up to 5. So that's going to be 2 and 3. And they're both going to be negative in order for us to end up with a negative 5 here. Okay, so I'm going to take and set each of these denominators. Each one of those cannot be equal to 0. So I'm going to get x cannot be 2 and x cannot be 3. Okay, moving on to the radical, we said that we can't take the square root of negative numbers. So I've got to make sure that this is a positive expression. So I'm going to set it up so that it has to be positive or equal to 0. So greater than or equal to 0. If I solve this, move the 1 to the other side, I'm going to get x has to be greater than or equal to 1/2. So from 1/2 to infinity. Okay, so here on these, a lot of times we say what x cannot be, and on these we say what x can be. Both are ways to write domain, so that's fine with that. Okay, letter E. I'm running out of space here a little bit, so I'm going to come over to the side to write my work. But this one here, we've got two things to worry about. One is we've got this denominator. So if we look at the denominator, we know that the denominator cannot be equal to 0. So that tells me x cannot be 5. So that's a part of my domain restriction. But I also have this radical. And so I know that whatever's underneath this radical has to be greater than or equal to 0. So basically looking at this, my domain on this, I'm going to combine these two together. So I'm going to say x can be greater than or equal to 0, but it cannot be 5. And on one of the homework problems that you'll have on WebAssign, you actually don't have to put this. If this had been like x is not negative 5, okay, then this would already be saying that, so I wouldn't have to include both. So just be careful that you're not like double saying the same thing on these. Okay, so here are 4 for you to practice with. So take just a minute and pause the video, practice writing your domains, and then advance to the next slide to see if you got those correct. Okay, these are the domains that you should have gotten. On the first one, we're not concerned with the numerator, just the denominator. So we want to factor that, set each factor not equal to 0, and then solve. And so we would have either x is not 2 or x is not -1, or if you want to write it in interval notation, it would look like this. Okay. On this one, we've got the radical and the denominator. So basically, we're going to say x, it has to be strictly greater than 0. We didn't do greater than or equal to because our denominator can't equal 0. So if I do this and set it up, then I get from 7 to infinity. So any number from 7 to infinity would work. Putting it into this, anything that's not in this interval is going to cause me some kind of error. Here I want to factor this denominator. I'll factor it and set each factor not equal to 0. So I find that x cannot be 2 or -2. And this one we're going to do, take the part under the radical and set it greater than or equal to 0. So when it's in the denominator, I set it greater than 0. When it's not in the denominator, I'll just set it greater than or equal to 0 because it's okay for it to equal 0 unless it's in the denominator. Okay, so moving on to simplifying rational expressions. Actually, I find this very easy if you can factor. Okay, so that's why it's so important in the previous sections that you learn to factor. Because if you can factor, simplifying and multiplying and dividing rational expressions will be one of the easiest sections that we do. Okay, our steps here are simply we factor and then we cancel like factors. And that's why the factoring is really where the work comes in. Canceling them is pretty simple. Okay, if we look at this example here, like I said, the first thing we want to do is factor. So on this one, if we're going to factor it, this is the difference of perfect squares. So we're going to have x plus 1 and x minus 1. On this one, we've got a trinomial with a leading coefficient of 1, so we don't need to do the bottoms up method. We just need the factors of 2 that subtract to give us 1. So okay, we need it to be a positive x in the middle, so I need this one to be positive and this one to be negative. Okay, make sure you have it factored correctly, and then when you look at this, we do see some common factors. We see that we have an x minus 1 and an x minus 1, so those are going to cancel off, and then we're just going to write our answer as what's left. Okay, so very simple if you're able to factor. Here's one for you to practice with. Go ahead and try this one, and then we'll take a look at it and we'll work it together. Okay, if we take a look at this first one, this is a trinomial without a leading coefficient. So we're just going to factor it. The factors of 6 that add up to 5 would be x plus 2 and x plus 3. And then here we want the factors of 15 that add up to 8. So that's going to be x plus 3 and x plus 5. Okay, we see a set of common factors here, and so we're going to be left with x plus 2 over x plus 5. It doesn't have to just be one set of common factors. It can be many. I will say if everything in the numerator cancels off, you need to leave a 1 in the numerator as a placeholder. Okay, so moving on to actually multiplying rational expressions. So we want to factor expressions completely, multiply the numerator and the denominator together, multiply your numerators together, multiply the denominators together, and then cancel your like factors. All right, so here we have this example here. This is a multiplication problem. All right, so this is a multiplication problem that we're going to be working with. So we want to go ahead and factor this. So we're going to factor this one. We need what multiplies to give us 3 and subtracts to give us 2. So we're going to have 3 and 1. We need the 2 to be positive. So we're going to set it up like that. Okay, this one we want what multiplies to give us 16 and adds to give us 8. So that's going to be 4 and 4. Here, when we go to factor, we have a GCF of 3. So I'm going to do 3, and that leaves me with an x plus 4. And then on this one, we'll have an x minus 1. On one like this, I would say go ahead and put it in parentheses just so that we keep it all together. So now, as long as we cancel top to bottom, it's okay to cross over and get these over here, or but we need to cancel one from the top with one from the bottom. Okay, so we've got one from the top, one from the bottom. So that leaves me with a 3, an x plus 3, and an x plus 4. So I'm usually just conventionally we pull a number out in front. So we'll have 3 and then x plus 3 and then x plus 4 for the denominator. And that would be our final answer. Okay, so here's another one for you to practice. So try this one and then we will take a look at your work. Okay, on this one we want to factor. We need the factors of 15 that subtract to give us 2. Okay, so we'll have 3 and 5. We need the 5 to be positive so that we end up with a positive 2x when we FOIL it back out. The bottom, we've got a difference of perfect squares, so we'll have x minus 5 and x plus 5. Here we have an x minus 5, and here we have an x minus 2. Okay, we'll group these two together, and then we'll cancel top to bottom. So we have an x plus 5 and an x plus 5. We have an x minus 5 and an x minus 5. So this is going to be x minus 3 over x minus 2. So you can see it's actually a little bit fun to go in and cancel all the factors out that are common. Okay, so moving on to dividing. The good news about dividing is there's one additional step, and that is if it's division, just like dividing any fractions, we have the same change flip or keep change flip. Some of you have heard it that way. I'm more familiar with the same change flip, but some will say keep change flip. But either way, we keep the first fraction the same. We change it from division to multiplication, and then we're going to flip this fraction here. Okay, so we'll have the reciprocal of that. Once we've done that, we cancel any like factors. And you can probably guess what the common mistake is here, and that is that people forget to flip. Okay, it's not that they don't know to flip, they forget to flip. So my advice would be flip it first, let that be your first step, and then go ahead and do your factoring and your canceling. Okay, so if we look at this one here, we've got division. So I'm going to go ahead and I'm going to just flip the whole thing. So I'll have x minus 4 and then x squared minus 4. I'm going to multiply that. I'm going to change it from division to multiplication, and then I'm going to flip the second one. Okay, from here, we want to factor everything. So obviously the x minus 4 is not going to factor. This is going to be difference of squares. So it's going to factor x minus 2x plus 2. This one we've actually factored a couple times. That's going to be x plus 2 and x plus 3. And here we're going to have, we need the factors of 4 that subtract to give us 3. So that's going to be 4 and 1. And we need the 4 to be negative to end up with a negative 3. Okay, always double check to make sure you have it factored correctly, because that's going to really mess up everything if you don't have it factored correctly. And some of these will require you to do bottoms up. These particular ones did not because they had the ones in front of them. But if you had like a 2 here, then obviously you'd have to do bottoms up to factor. So just because we haven't seen any examples like that doesn't mean you won't encounter some. Okay, so now we're ready to cancel top to bottom. So we have an x minus 4 in the top and the bottom. Here we have an x plus 2 top to bottom. And so that's going to leave us with an x plus 3, an x minus 2, and an x plus 1 for our answer. Okay, that takes us to these additional practice problems that I have put here at the end of the section. So I would like for you to pause the video and try each of these four. One thing, this is another way of doing division. So if you think of it, this is like your first fraction and this is your second fraction. So it's the same as having it written with a division sign. So go ahead and try each of these four and then advance to the next screen in order to see the answers on this. Okay, on the first one here, you would factor, and this one you would need to do the bottoms up method in order to get it factored. And then you can cancel the y plus 3's out, and you'll just have y minus 6 over 2y plus 1. On the second one, you want to factor. One thing here, you've got a GCF that you would want to factor, and this one you want to factor with a GCF as well. When you cancel top to bottom, you're actually left with an x squared over x, which we could simplify to just be x. Okay, moving on to problems 3 and 4. On problem 3, when you factor and look at this, everything in the numerator cancels out, but instead of not writing anything, we have to write a 1 there as a placeholder, and that leaves us with the 2x minus 5 and the 3x minus 2 in the denominator. And then on the last one, this is division when it's written like this. So we've got the first fraction divided by the second fraction. So we're going to do keep, change it to multiplication, and then we're going to flip the second fraction. And then we'll cancel, if we haven't already, it really doesn't matter if we factor here or we factor after we flip it, but we're going to cancel top to bottom, and we end up with x minus 2 over x plus 1. Okay, and so that takes us to the end of our lesson for today.